Now, speaking of traveling out into deep space, yeah, you already mentioned this a little bit. You made a beautiful video called "The Journey to the End of the Universe," and sort of at the start of that, you're talking about Alpha Centauri. So, what would it take for humans, or for human-like creatures, to travel out to Alpha Centauri?
There's a few different ways of doing it, I suppose. One is, it depends on how fast your ship is. That's always going to be the determining factor. If we devised some interstellar propulsion system that could travel a fraction of the speed of light, then we could do it in our lifetimes, which is, I think, what people normally dream of when they think about interstellar propulsion and travel. That you could literally step onto the spacecraft, maybe a few years later, you step off on Alpha Centauri B, you walk around the surface and come back and visit your family. There would be, of course, a lot of relativistic time dilation as a result of that trip. You would have aged a lot less than people back on Earth by traveling close to the speed of light for some fraction of time. The challenge of this, of course, is that we have no such propulsion system that can achieve this. So,
but do you think it's possible? Like, so you have a paper called the Halo Drive, fuel-free relativistic propulsion of large masses via recycled boomerang photons. So, do you think, first of all, what is that? And second of all, how difficult are alternate propulsion systems?
Yeah. So before I took in the Halo Drive, there was an idea, because I think the Halo Drive is not going to solve this problem. I'll talk about the Halo Drive in a moment, but the Halo Drive is useful for a civilization which is a bit more advanced than us, that has spread across the stars, and is looking for a cheap highway system to get across the galaxy. For that first step, because just to context that, the Halo Drive requires a black hole, so that's why you're not going to be able to do this on the Earth right now. But there are lots of black holes in the Milky Way, so that's the good news. So we'll come to that in a moment. But if you're trying to travel to Alpha Centauri without a black hole, then the most, there are some ideas out there. There was a Project Daedalus and Project Icarus that were two projects that the British Interplanetary Society conjured up on sort of a 20, 30-year timescale. And they asked themselves, if we took existing and speculatively but realistic attempts at future technology that are emerging over the next few decades, how far could we push an interstellar travel system? And they settled on fusion drives in that. So if we had the ability to essentially either detonate, you can always imagine that kind of nuclear fission or nuclear fusion bombs going off behind the spacecraft and propelling it that way, or having some kind of successful nuclear fusion reaction, which obviously we haven't really demonstrated yet as a propulsion system, then you could achieve something like 10% the speed of light in those systems. But these are huge spacecrafts, and I think you need a huge spacecraft if you're going to take people along. The conversation recently has actually switched, and that idea is kind of seen as a little bit antiquated now. And most of us have kind of given up on the idea of people physically, biologically stepping on board the spacecraft. And maybe we'll be sending something that's more like a microprobe that maybe just weighs a gram or two. And that's much easier to accelerate. You could push that with a laser system to very high speed, get it to maybe 20% the speed of light. It has to survive the journey. Probably a large fraction of them won't survive the journey, but they're cheap enough that you could maybe manufacture millions of them. And some of them do arrive and are able to send back an image, or maybe even if you wanted to have a person there, we might have some way of doing like a telepresence or some kind of delayed telepresence, or some kind of reconstruction of the planet which is sent back, so you can digitally interact with that environment in a way which is not real time, but representative of what that planet would be like to be on the surface. So we might be more like digital visitors to these planets. Certainly far easier practically to do that than physically forcing this wet chunk of meat to fly light years across space to do that. And so that's maybe something we can imagine down the road. The Halo Drive, as I said, is thinking even further ahead. And if you did want to launch large masses could even be planet-sized things. In the case of the Halo Drive, you can use black holes. So this is kind of a trick of physics. I often think of the universe as like a big computer game, and you're trying to find cheat codes, hacks, exploits that the universe didn't intend for you to use. But once you find them, you can address all sorts of interesting capabilities that you didn't previously have.
Yeah.
And the halo drive does that with black holes. So if you have two black holes, which are a very common situation, a binary black hole, and they're spiraling towards each other, LIGO's detected, I think, dozens of these things, maybe even over 100 at this point. And these things, as they merge together, the pre-merger phase, they're orbiting each other very, very fast, even close to the speed of light. And so Freeman Dyson, before he passed away, I think in the 70s, he had this provocative paper called Gravitational Machines, and he suggested that you could use neutron stars as an interstellar propulsion system. And neutron stars are sort of the lower mass version of a binary black hole system, essentially. In this case, he suggested just doing gravitational slingshot, just fly your spacecraft into this very compact and relativistic binary system. And you do need neutron stars because if there were two stars, they'd be physically touching each other. So the neutron stars are so small, they're like 10 kilometers across. They can get really close to each other and have these very, very fast orbits with respect to each other. You shoot your spacecraft right through the middle, like flying through the eye of a needle, and you do a slingshot around one of them, and you do it around the one that's coming sort of towards you. So one of them be coming away, one will be coming towards you at any one point. And then you could basically steal some of the kinetic energy in the slingshot. In principle, you can set up to twice the speed. You can take your speed, and it becomes your speed plus twice the speed of the neutron star in this case. And that would be your new speed after the slingshot. This seems great because it's just free energy, basically. You're not doing any, you don't have a nuclear power reactor or anything to generate this, you're just stealing it. And indeed, you could get to relativistic speeds this way. So I loved that paper, but I had a criticism. And the criticism was that this is like trying to fly your ship into a blender, right? This is two neutron stars, which have huge tidal forces. And they're whipping around each other once every second or even less than a second. And you're trying to fly your spaceship and do this maneuver that is pretty precarious. And so it just didn't seem practical to me to do this, but I loved it. And so I took that idea, and this is how science is. It's iterative. It's you take a previous great man's idea and you just sort of maybe slightly tweak it and improve it. And that's how I see the halo drive. And I just suggested, why not replace those out for black holes, which is certainly very common. And rather than flying your ship into that hellhole of a blender system, you just stand back and you fire a laser beam. Now, because black holes have such intense gravitational fields, they can bend light into complete 180s. They can actually become mirrors. So, the sun bends light by maybe a fraction of a degree through gravitational lensing, but a compact object like a black hole can do a full 180. In fact, if you went too close, if you put the laser beam too close, the black hole would just fall into it and never come back out. So you just kind of push it out until you get to a point where it's just skirting the event horizon. And then that laser beam skirts around and it comes back. Now, the laser beam wants to do it is doing a gravitational slingshot, but light, photons can't speed up, unlike the spaceship case. So instead of speeding up, the way they steal energy is they increase their frequency. So they become higher energy photon packets, essentially. They get blue shifted so that you send maybe a red laser beam and it comes back blue. It's got more energy in it. And because photons carry momentum, which is somewhat unintuitive in everyday experience, but they do. That's how solar sails work. They carry momentum. They push things. You can even use them as laser tweezers and things to pick things up. Because they push, it comes back with more momentum than it left. So you get an acceleration force from this. And again, you're just seeing energy from the black hole to do this. So you can get up to the same speed. It's basically the same idea as Freeman Dyson, but doing it from a safer distance. And there should be of order of 1 million or so, or 10 million black holes in the Milky Way galaxy. Some of them would be even as close as sort of 10 to 20 light years when you do the occurrence rate statistics of how close you might expect feasibly one to be. They're, of course, difficult to detect because they're black, and so they're inherently hard to see. But statistically, there should be plenty out there in the Milky Way. And so these objects would be natural waypoint stations. You could use them to both accelerate away and to brake and slow down.